Okay, so I want to finish up the proof of the inverse function theorem, and then discuss the implicit, and then show you why we care about this stuff, other than the examples that we've already done. So we got as far as, yesterday, proving that the inverse function was continuous. And we actually got, we ended with G continuous because we had an estimate that said G of y minus G of z is at most twice y minus z in magnitude. Right? That's where we were at the end last time. So, what's left to prove? G is differentiable and that the derivative is continuous. So, it remains to show G is differentiable. Alright, so you already believe, so Daniel is trying to do an end run around all this stuff by saying, let's use the chain rule. Until we pointed out to him that assumed a few things. But if it were in fact differentiable, we know if G is in fact differentiable at some point y, then we have no choice for what its derivative can be. There's only one choice. There's only one option for what the derivative of G at y can be. Right? Because you have the chain rule, which says that fog is the identity, or goff is the identity, either one. If you knew it were differentiable, then you would know that the derivatives had the inverses of each other. And you do them at the appropriate point, right? So dg of y has no choice but to be the inverse of df at g of y.
Is I be the identity?
Yeah, I didn't write I because that looks like a matrix. This is for functions.
Okay.
So that's why I didn't write I. So this is the only option for what the derivative can be by the chain rule. Right? So write down the chain rule is df at g of y composed with dg of y has to be identity matrix. So it has to be the inverse. So all I have to do is, remember when we recall back centuries ago, what's the definition for a function being differentiable?
If that limit is 0.
What limit? Some limit, but what there has to be what that goes into the limit?
X plus h minus.
No, I'm not asking for the whole.
A linear map.
There has to be a linear map that gives the best linear approximation. And you only have one candidate for the linear map. So all we have to do is show that candidate satisfies the definition. So let's let A equal df, at g of y, and let's show.
Wait, so we're proceeding just assuming G is differentiable at this point?
No,
Okay. So
no.
Okay.
So but I'm saying the definition of differentiable was that you have to find a linear map that has a property. I'm telling you, we know what the linear map has to be, and now we have to prove it has the property.
You need an inverse sign, right?
Oh, I wanted to.
Oh, really? Okay.
So we need to show the limit, and for some reason that you will understand in a moment, I'm going to write k instead of h. G of y plus k minus g of y minus the best linear approximation, the alleged best approximation is going to be given by A inverse times k, and you divide by the length of k, and you want to say the error goes to 0 faster than k approaches 0. So we need to show this is true. Agreed? So let's draw a little bit of picture so we don't lose our mind completely here. So here's x, it's mapping to y. So g of y is going to be x again. And I might as well take y plus k here, and it maps back to something near
X plus H.
Near x, so I'm going to call it x plus h. So x plus h is going to map to there, x is going to map to there, and so g is going to map them backwards. So let's set h equal to what?
G of K.
Say it? No, we need to just say that. How do I get h? If I know x plus h, how do I get h?
Subtract h. Oh, I mean subtract x.
Subtract x, right? So this is g of y plus k minus g of y. Right? This is x plus h minus x. Well, then this limit is equivalent to saying, well, I don't know. I don't like inverses much. What's the point of inverses anyway?
To get the identity.
But I could get rid of the inverse by doing what with the whole thing? Multiplying by a. Does that affect whether the limit is 0 or not? No, because linear maps are continuous. So a times something goes to 0 if and only if the something goes to 0. Remember? So using the fact the linear maps are continuous, so blah goes to 0 if and only if a blah goes to 0. Is that okay? I'm going to just take a times the numerator. I'm going to take this whole vector in the numerator and a it. So I'm going to have a. Now what's g of hy plus k minus g of y here?
H.
That's h. Or minus k, because I multiplied the whole thing by a over magnitude of k.
So you can change the, well, it's still k going to 0.
Still k going to 0.
Is A not singular here?
Yeah.
Okay.
Remember, our whole hypothesis was that the derivative of f was non-singular. Okay. Well, what's k? AH minus, what is k? Yeah, k is y plus k minus y. So that's f, exactly as Ken just said, that's f of x plus h minus f of x. This looks mighty familiar. What does it look like? Definition of f. Except it's off by a minus sign. The definition of the derivative of f was this minus this. Well, come on, give me a break.
Is it still over K?
So Cameron is reiterating Daniel's point from a minute ago. This is okay, magnitude of k. What do I need to get the definition of the derivative of f?
Magnitude h.
The magnitude of h. So what does the method of wishful thinking suggest we do?
We have over there
K.
g of y minus g of us multiplied by y minus z, so no magnitude k is less than 1/2 magnitude of h.
Okay, okay, hang on a second, Ken. We know limit is h goes to 0, so h goes to 0 of f of x plus h minus f of x minus ah over magnitude h is 0. So let's for a minute not worry about this.
Do we know that because the derivative, we set the derivative at the origin to be 0? Or no, just because it has a derivative, yeah.
F is differential on this whole neighborhood. So what is true about the numerator that we have over the denominator we have? So we have a k. We know it with an h.
We just multiply by k over
The top, you should multiply just times -1.
Yeah, right. I have multiplied by -1 because it all hurt. So if I divide by magnitude h, I have to then multiply by magnitude h. Now, somebody in the room ought to complain. Did I just multiply and divide by something illegitimately?
No, because it's approaching 0. It's not actually 0.
K is approaching 0. How do I know h isn't ever 0?
Because it was 1.
Yes, it's because of 1 to 1. So we know on our neighborhood of our point that f and g are both 1 to 1, so the only time h can be 0 is when k is 0. So this is legit. So there's a comment here, legit. H is not 0 when k is not 0. Okay. Now, so there's still an issue about h going to 0 versus k going to 0. But, all right, Cameron, what do you want me to say?
I want us to go back to g of y minus g of z is less than or equal to 2y minus z.
So,
When we have a function relating g of y and g of y plus k and f of x, and that makes math.
so you're saying if I take x plus y plus k minus y,
Yeah.
you get a k here, and you get the h there. So Cameron points out that the star here is telling us that h is actually less than or equal to 2k in magnitude. So what does that mean about this fraction?
It's less than or equal to 2.
Okay. Doesn't have a limit necessarily, but it's less than or equal to 2, it's bounded. What is this doing?
Going to 0.
So if you take something that's going to 0 times something that's bounded, it still goes to 0. There's only one thing left to justify, and it's still coming from Cameron's thing. This tells us that as k goes to 0, what must h do?
Also go to 0.
Right? So this tells us that k going to 0 implies h goes to 0. So when I take the limit as k goes to 0, in fact, I get to use the h is going to 0. Therefore, this goes to 0 as h goes to 0. Hence, as k goes to 0, and this part is bounded. So the product is going to 0. Everybody okay with this? So we are differentiable. Now, the the very last piece is actually one of my favorite arguments. I know you're tired of hearing that.
Is this
Or
class,
Wait,
how
your
do we,
favorite things?
how do we know that as h approaches 0, k has to approach 0?
I didn't need that.
Well, you just read that.
No, it's
Or
gonna,
am I reading it backwards?
well, no. This goes to 0 as h goes to 0.
Sure.
Hence, since k going to 0 forces h to go to 0,
Oh, okay. Okay. Thank you.
So we still, if we had written it all the way out as a limit of k approaching 0, still.
yes.
Okay.
But I would speak, I mean, so in principle, if you're going to be pedantic with epsilons, you'd have to have a chain of epsilonics in here related to h and k. But I'm sparing you that, and I'm sparing me that. The logic is correct. I mean, it's also true the other way around, that as h goes to 0, k goes to 0, because of continuity. Okay. So,
Sorry, where did we get?
H still has to go to 2K.
the thing I just erased. Last, y is g c1. So here's the formula for dg. Why does this tell you that this varies continuously with y?
Well, we know df is continuous because we said f was c1. Then
So we knew g is.
So dg is a composition of how many functions here? What do you start with a y, you first do what?
g.
G,
And do the inverse.
df.
then you do df,
Then
and then you do inverse. So it's a composition of inverse with df with g. You agree with that?
What does it mean, DF composed?
It means this. First, take your y, plug it into g, plug that into the df function. I don't mean multiply by, I mean evaluate df at the point g of y. So I have a composition of three functions,
And they're all continuous?
and they're all continuous.
So it's
df is continuous, g is continuous, because we already proved that. And inverse, why is matrix inverse continuous?
You're like the matrix inverse like a non-even.
We showed it. I had a problem.
You guys proved this in homework.
Wasn't it?
With
the general six.
General linear set or whatever.
Yes. This was number 6 in last week's homework.
Because that is in the set of, yeah.
Right? You proved that taking inverse was a continuous function on a set of invertible matrices. That was what you did. So you actually proved this in homework, but actually, I'm going to trump your homework.
I thought we just proved that the general linear set was open.
Yeah.
Now you actually
In the
proved...
text, I think it talks about it being continuous.
No, but you actually, you showed... Oh, maybe you didn't. Maybe that was the next problem that I didn't assign.
Thank you.
Okay, you're right. Okay, wrong. I didn't assign the next problem.
What's,
But I'm still going to trump you.
what symbol is that?
That's an iota.
Okay, so.
But remember, we proved in chapter 7, which we've done before this, that taking matrices and taking the inverse is what kind of function?
One.
Left multiplication by dividend.
No. What, we have a formula for A inverse that you learned in chapter 7.
Oh, it's polynomial.
Close.
See, that isn't it polynomial?
No.
A inverse, what was the formula for the inverse?
One of the determinant of a cofactor matrix.
So the entries of A inverse are rational functions in the entries of A.
And because term of A is not 0.
Yes. If this is a polynomial in the entries of A, these are all polynomials. So A inverse is a rational function. Hence, smooth, C infinity. It's not just continuous, but it's actually infinitely differentiable in the entries. Okay. And so this is really cool. So the remark actually is indeed, it now follows that if f started off ck for some k bigger than 1, then g is ck
So G gets all the benefits of
of f. Can you give me the argument from this? Suppose f were C2.
Don't you just add in another DF?
No, I'm not going to take any derivatives. I'm just going to use this equation.
Oh yeah, because G is continuous and...
No, but if f is C1, we know g is now C1.
Okay.
No, I don't want to take derivatives. You're not playing nice. I do not want to take derivatives and have infinite chain rules for higher derivatives. Suppose f is C2. Then we know f is C1. So we know g is C1. So this is C1. This is C1 because f is C2. And inverse, we just said, is C infinity. So it's certainly C1. Composition of C1 functions is C1. Therefore, dg is C1, so g is C2. How do we do it in general? What's the magic word?
Induction.
Induction. No, you're not responsible for this proof that we just did.
Wait, which proof?
What I just said and didn't write on the board. I knew what you thought. Okay,
So we are responsible for the big one.
so basically, it's a bootstrapping argument. That's the language that a lot of people in computer science use. You work your way up one and then another and then another. That's what induction is. So, I think it's really cool to think about it. It's like, so the key thing is that f is ck is equivalent to saying df is ck minus 1. So you basically show this thing is ck minus 1 inductively. Okay, so that's the end of that proof. I have one other easy proof to do, and that is, okay, now we can deduce the implicit function theorem.
So we're done with the inverse.
I'm done with the proof, man. There, I'm done. So, having done all this hard work, you'll be relieved to know that the implicit function theorem can be proved in the rest of this board. Now, of course, if I rewrite the whole statement of the theorem, I'll fill up all the board, so I'm not going to do that. You already have it in your notes and in the book. So the implicit function theorem, remember though, the picture is this. I'll draw the picture. And then I'll embellish the picture. We have a function, capital F, mapping Rn, which we split up this way. Remember, this was our x and this was our y. So the y matched in dimension of m. And we looked at where f was 0. And there was the hypothesis that I almost forgot, that the partial of f with respect to the y variables, that square matrix at your point, was what? Non-singular. And the picture of the implicit function theorem was that here we have zero And you're looking at all the points that capital F maps to 0, at least near a certain point. So we're looking at the pre-image of 0, and what I'm claiming is that it looks something like that, that has the same number of dimensions as our leftover, this number of dimensions. And we're taking a point x naught, y naught, where the partial respect to y is non-singular. So it's not going to be a point that looks like that, it's going to look like this. And we're saying there's a neighborhood of that where we could write it as a graph. So here's what I'm going to do. I want to apply the inverse function theorem. So be creative, create a function, little f, to whom the inverse, the chalk tray again, function theorem applies. So what do I need to have the inverse function theorem? What's supposed to happen in that picture?
Just be able to,
Louder?
like a G to map back.
No, but what for the setup of the inverse function
Well, you
theorem?
need an open set, which you've got.
And what?
You need to
I need Rn to Rn. This guy's missing some coordinates, man. So you need to put a cross Rn minus m over here. You need to take this picture and give it an Rn minus m, so that we're mapping n to n.
Even those dimensions won't come into play. Right?
Well, I'm going to make those dimensions. So I want to create a function f, little f, of x and y that now maps to n dimensions. The m part of it, I will already use what I've got. I've got f, capital F, that maps to the Rn part, but I need something in the R minus n minus m.
Can you just do 0?
I could. But here's your goal. You're supposed to be creative. And you're supposed to, what's the hypothesis for the inverse function theorem? The derivative of little f needs to be non-singular. So the question is, what can I put here so the derivative of this will be non-singular?
1.
I did x.
Who said 1? What does 1 mean?
Can you put an X there so it goes to identity?
So you guys are suggesting putting x there. Let's see if that's a reasonable thing to do. You take d of little f, d of little f, what does that now look like? So it's got the, this part is m by m, and that's got the df dy in it, which we know is, so think back to the linear algebra stuff you've been doing over the past. What do you want to make this matrix be non-singular? We don't know, so we don't know about this part.
Upper left. You want it to be non-singular.
You want this to be non-singular and you'd like this to be 0. Because if this isn't 0, this stuff comes into play and then you don't know what to do. But if you make this be a 0, then this doesn't matter, and all you need is that this is non-singular.
So if you took respect to x, it'd be 1 and 0.
So if you put an x there, the derivative is the identity in that corner, and that's as easy as it could be. Make sense to everybody? There's another reason you're going to like having that x there. All right, so do you agree now that by hypothesis, if I make this function up, df at the point x naught, y naught, it's definitely non-singular by everything you guys have done on determinants for homework. Right? So, what does that mean? Well, it means that if I take this mapping, what is the picture now? Where does this blue stuff map? It doesn't map to the dot anymore. Where is it mapping? So all the f values are still 0. But what about in the first coordinate?
That's everything. So it's
So it's mapping into whatever the x's are doing. You're keeping track of where the x's are here, and you're moving like this in the x space, right? Corresponding to whatever's happening here. So if you go along here, you go blah, 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 like that. But the point I'm interested in, this 1 point x naught y naught is mapping over here somewhere. And what's the mapping doing near this point? It's going like this in a non-singular way. So it's mapping a neighborhood of this point to a neighborhood of this point. Because of the inverse function theorem, you get an open set mapping to an open set in a one-to-one C1 way. So there's a local inverse. G for the function, maybe I'll call it capital G to be consistent. No, little g for f. So this is now no longer capital F, this is now little f, because I've changed the range of the function, changed the function. Can you see how I can get back to what capital F of x, y is doing? If I want to get back to the function capital F,
compose little f of g, and then
so what do I get if I do
look at it
g
component by component.
of f? What's the definition if you have an inverse?
Well, you get infinity.
I get xy. Now, what points here are going to map to this blue set here? I'm interested in recovering my level set. What points should I feed here to go back to the blue curve here? Oh, I should be where y is 0.
What's y in this case?
So let's do g of x comma 0. What does that give me? So if I start at a point x here and plug in the y coordinate here is 0, and I do g of it, I bet you it's going to take me back to this. Well, let's see. It has to be, the first coordinate has to be x, because what is this mapping doing in the first coordinate? It's just preserving it. So the inverse function takes stuff back to the same x. The second coordinate is something or other. I don't know what it is. I'm going to call it phi of x. Wherever this goes, it depends on where I started, which was of the form x0. So it depends only on x.
So that phi of x determines kind of before at the green point we have in the first graph on the left. Or like
Right, so what I'm saying now is, I'm now telling you how to write this thing as a graph of a function phi. Here's how you define phi. Then the claim is, in our neighborhood, xy is in f inverse of 0 if and only if y is phi of x. Well, look, if I'm in f inverse of 0, that means capital F of this is 0. That means when I plug it in little f, when I plug xy into little f, I get x0. And then that means that if I do g of that, I go back to where I started, which was a point xy where f of xy was 0. So at this point, if I do f of it, I get 0 because f of x, if I do f of this, that's f of g of x 0 by definition. This is g of x 0. And f of g of something is x is the something, is x 0. So little f of this is x 0. That means this piece is what capital F is doing. Little f is x capital F. So if I get 0 here, that's capital F. So basically, all we're saying is this blue stuff mapped to the horizontal stuff. The inverse maps the horizontal back to the blue, and that gives you the blue as a graph. Why is phi C1? I'm still fitting it on the board. Well, what we know G is, if f is C1, the local inverse is, so G is C1. So if you do a C1 function of x0, you get a C1 function of x. This is a C1 function, so whatever you feed in, it's going to be a C1 function of the inputs. So it's a C1 function of x. And the proof. All right, you've seen some real theorems, guys.
I've seen fake ones.
You've seen some fake ones too. All right. Yes, sir.
So should we put like a big star by this theorem?
I would say what I've made you accountable for in homework, you might, in terms of understanding how to set up and apply a mean value inequality and contraction mapping, you're responsible for understanding that. You're not responsible for reiterating a whole 2-day proof. Fair enough?
Fair enough.
All right, so why do we care about this stuff? Aside from the fact that it's one of the most important theorems in all of mathematics. Well,
Other than that, it's in the book.
Probably, yeah. Because it's going to be on the test.
yeah, that's right.
Really, at this point.
So this is the paraphernalia you need to actually understand C1 mappings in their general context. And remember where we're headed. We've done multiple integrals. We've done derivatives last semester. And we're still trying to figure out how we can tie them together. So we still don't really have the fundamental theorem of calculus yet, other than as you used it in one dimension when we did iterated integrals. So where we're headed is we want to be able to integrate on manifolds and have a version of the fundamental theorem.
Meaning have manifolds be our region where.
Right. So we want to be able to integrate not just on open subsets of R2, or domains in R2, or domains in R3, or domains in R4, but I want to be able to integrate over spheres. And if any of you have done any physics, I guess Michael had class today, if anyone has done any physics, you actually know that that's physically important to do so. Same thing with chemistry, same thing even some places in econ, I would wager.
On spheres or on the surface of a sphere?
Yeah, sphere means surface, right?
Oh, yeah.
And more general things than spheres. Tori,
Little weird.
paraboloids.
Blob shape. Blob shapes.
So I want to have a more rigorous notion of what a manifold is. You guys met the word last semester. You weren't very friendly. You walked away in a huff.
Ran.
Ran away, yeah. It's like the poor thing hadn't showered in weeks. So we want to do a new approach and actually give you a better shot at having it make sense now that we've been through all this stuff. So here's the game plan. I want to give you 3 equivalent definitions of a k-dimensional manifold. Actually, what dimension do I use? I've forgotten.
Why are you putting definitions in quotes?
Hush.
It's a fake definition.
Is it like a Jeopardy category?
Yeah, I want to say k. K-dimensional. So, I emphasized last semester that we had that linear algebra was giving us two ways to understand linear subspaces. What were the two fundamental ideas? Explicit and implicit. So that is persisting here. Except I'm actually going to make it into 3 versions. And
Are these the 3 definitions?
there are going to be 3 definitions. I'm going to need more room. I'm not going to put them here. But so implicit you're used to because we've been doing that a lot, and it has a lot to do with the implicit function theorem. What's an implicitly defined set? It's one that's given by equations. So this is basically looking at M near each point P is given by saying some equations hold. So I'm going to write down official definitions before we're done today. Explicit is exactly what the implicit function theorem says you get. Writing it as a graph. So an explicit representation of a high-dimensional surface is going to be, it's a graph with respect to certain independent variables, x. So M near each point P looks like y equals phi of x, where you choose some k coordinates for your x, and these are the remaining coordinates. So I'll write this all out carefully in there. What's left?
Parametric.
What does parametric mean?
We write all of the variables with respect to some other variable like t.
Right, exactly right. So you're going to represent M, again locally, by parametric equations, where you give the points as g of some parameters u, where there are k parameters, because we have k degrees of freedom. So Davis was thinking back to curves, which we did parametrically, where there was 1 degree of freedom, so you have a single parameter t. We did do a few things, didn't we, with surfaces? I don't remember now. Polar coordinates. All right, so this is the setup. I'm going to give you rigorous definitions, and then what we will do tomorrow is do examples and how you see how to go back and forth among these. But roughly speaking, before I write down the definitions, I am going over to use up my few extra minutes today. Do we know any way to go back and forth among these just without being pedantic yet?
Yeah, how about explicit
You
implicit?
subtract y from both sides.
Aha, so you see how to get this way.
In very simple scenarios, you know how to do it. It's parametric and back.
Right, say again?
Very, very easy scenarios, you know how to get from parametric to back. Like,
Well, if you have it explicitly, can you parameterize it?
Yes.
yeah.
So explicit implies implicit by taking, exactly as David said, taking y equals phi of x, rewriting that and saying, and you guys did this last semester when you figured out how to find gradients to level sets, and you saw how to use it. I don't remember whether you did y minus phi of x or the other way around, it doesn't matter. Okay, how do we get parametric? Well, what do I use as my parameters? If I have a graph, I can can write it parametrically in terms of the parameters x. So there's my parameterization in terms of x as parameters.
In our parameterization, we were
Yeah.
parameterizing x.
Well,
So we choose what we want.
I meant everybody for x, so let me take that out of there. You're representing the whole surface in the form G of U.
So would that be the graph of G of U?
No,
It would.
this would be the graph of phi. But for example, what's a parametric representation that isn't a graph? How about cosine t, sine t for the circle? That parameterizes the circle. That's a parametric representation.
So would the circle be the image of G?
Yes.
Image.
Yeah. Now you could locally write the circle as a graph. So you could parameterize it by x square root of 1 minus x squared. That would be a parametric representation as well. And that's represented as a graph. But that's still a parameterization. All right, any more connections we can make among the definitions? I already gave it away.
Yeah. If you go, I guess, implicit, explicit, if it's
It works
the
out.
variable, yeah, if it works out well, the variable's like, you just put one on the other side.
Well, but what if it doesn't work out well?
I don't know.
What tells you to go there?
Can you put the implicit function?
Right, that's the implicit function there. So, I haven't given you any hypotheses here yet. Part of the definitions is actual hypotheses. But this direction, saying if you have f equals 0 with some hypotheses, then you can write it as a graph. That's exactly the implicit function. So, implicit implies explicit is exactly the implicit function thing that we just did. So we aren't quite done knowing they're all equivalent, but we're close. What's missing?
Parametric, yeah.
You have to be able to get from parametric to one of the other two. So you have to either be able to get from parametric to explicit or parametric to implicit. And I'm not going to give you that proof. It's actually done in the book. I forgot which one is done in the book. This one is done in the book. And parametric implies explicit is one of your challenge problems, which is number 14.
If you know that it goes to implicit, can you just then put implicit to explicit? He means directly.
Yeah, I mean directly. So I mean, if you want to be maximally efficient to prove three things are equivalent,
Proof every variance.
no.
Or just
What? Come on, computer science people. How many theorems do you have to prove three things are equivalent? Three. No, you have to prove three implications. If you prove this implies this implies this implies this, you've got they're all equivalent. Or if you prove this implies this implies this implies this, they're all equivalent. So you only need three. Unfortunately, though, the ones we've already done don't make the full cycle, so you have to do one of these two to be complete. And I'm actually not going to do it. I'm sparing you that. So, all right, so what I'm going to do for the end of today is actually write down what the definitions are officially, and then tomorrow we're just going to write examples. And in case you're keeping score, Monday we start chapter 8. And then I'll answer questions if you have questions on this stuff. Okay, so the explicit definition. So here's the basic thing. M sitting inside Rn is a k-dimensional manifold if for every point P there is a neighborhood W, so that, and then I'm going to put the three things. So here you have your manifold. And I'm saying for each P, you can find a neighborhood in Rn, so you can find an open set in Rn, so that the piece of M near P in that neighborhood, so in this case it would be something like that, and my neighborhood would look like some open chunk of R3, this picture. So it would be going down below and coming out above, and that would be my neighborhood. So you have the surface in R3, and you have a ball around the point P. And the ball intersects the surface in a piece of the surface.
So manifolds aren't solid.
No, not generally. They're k-dimensional sitting inside Rn.
Right.
If it were n-dimensional sitting in Rn, it would be solid.
So K can be up to N,
Yeah,
but no more.
right.
Is that what makes sense?
So that, okay, so for the explicit definition, we can write points of M intersect W, the part of M inside of W, as y equals phi of x, phi of C1, and here x is some collection of, this is why I don't like writing this out pedantically. You pick k of your coordinates. So I1 to ik are between 1 and n. So pick some k of our standard coordinates. So it might not be x and y, it might be z and y, or it might be x and z. Pick some of k's coordinates, and y are the remaining ones. So you're picking some k of our standard coordinates and writing the remaining n minus k coordinates as functions of them.
So basically you can make N minus K coordinates dependent on K.
So that was our picture that we were doing with the implicit function theorem, where I had, except the letters are different, but I had m this way and n minus m this way, so the n minus m would be the k.
This is the result of
If I'm going backwards from here to here, yes. Right, that's right. All right, so that's the explicit. The implicit is that there is some function we have a C1 function f mapping this open set W to R n minus k. So I have to give n minus k equations to define something k-dimensional, so that M intersect W is the free image of 0. So those are the equations that are giving M in the set W. And the hypothesis is the rank of the derivative of f at the point P is n minus k. The mapping n space to n minus k, it's full rank, as Daniel said. You have independent equations at the point P, and that implies they're true locally.
So we could have said if we wanted to that just that that was not singular.
No, 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 this is not a square matrix.
Oh, right.
So I'm saying there's some choice of columns that makes a non-singular matrix. When we set up the implicit function theorem, we put them all at the end. Here I'm saying they can be anywhere.
Okay.
So again, I will do lots of examples for you tomorrow.
Can rank be greater?
No, because you're mapping to n minus k. So,
Right, okay, yes.
so that's the biggest it can be. last definition, and we'll close up shop for today. The last definition is the parametric. And this one seems totally intuitive, like parameterizing curves is intuitive, but there's a little bit of technicality. So there is an open set U in Rk, a function, I guess I should say there are, a C1 function G mapping U to Rn, so that G of U, all the points you map to are going to be the part of M inside of W. We're going to have G is C1. I said it was C1. We're going to say G is 1 to 1. C1, so you're parameterizing by some function that gives you maybe not quite all the circle, but most of it in this case. But you better have a rank condition here.
So G being 1 to 1 means every point in M intersected with W
Is hit by exactly 1 point. Exactly 1 point. The rank of the derivative is now supposed to again be maximal, so it's going to be K for all U. And then there's this technical condition, which I will draw you a picture to explain. The inverse function of G, going backwards from here to here. So this is a mystical condition, you'll see it in a minute. Mapping M intersect W back to U has to be continuous. And you say, why in the world is that there? So this is what I'm going to end today with.
Wait, is that, do we not know that?
Nope.
Okay. You can tell like a random.
Here's what can happen with parametric equations.
But G is C1.
G is C1. Has anyone in here heard of a Lissajous figure from physics?
Is that
Well, we want all those accelerators here. So here's an example. Here's G mapping negative pi to pi to R2. And I worked very hard to get this. G of t is sine of t, sine of 2t. So you actually can see this curve appearing on oscilloscopes if you do the right thing. What does this curve look like? Well, what's G of 0? I can do that one.
0.
0.
Sorry, there's one still one.
And in fact, if you think about the derivative of this thing at t equals 0, the derivative is cosine t, 2 cosine 2t. It's headed uphill with slope 2. Now, what happens when I hit pi over 2?
There's that 1, 0.
1, 0. And then as I come back, go up to pi, it comes back to 0, 0. So what this thing does is it goes uphill, comes down here, bends around, and heads back up like that. And if you go back this way, it goes down, up, around, and heads to here. So it's heading to the origin as you go to the extremities, but it is never going there again. As you go out to here, it comes in there, it comes in here, but it doesn't hit 0. So you see roughly a figure. Is that a one-dimensional manifold? No. Does it look like a one-dimensional manifold at that point? No, it doesn't. It looks like an X. That is not a graph over the x-axis, and that is not a graph over the y-axis, so it fails definition 1. But the map is still 1 to 1. Derivatives got rank 1 everywhere. What went wrong? Yeah, it's 1 to 1, because you never come back and hit there. That would happen if you put in pi or you put in negative pi, but you don't, it's open.
Okay.
Well, because the inverse.
So the inverse is not continuous, because if you go back from here to here, it's not a continuous function. Take a neighborhood of this point. Where does the origin map? It maps there. Well, do all the points near the origin here map close to this? No, you get some that are close and some that are very far away. So G inverse is not continuous. And that's why that condition is there. It stops this from happening.